And then I've also got something really kind of cool that I'm going to share with you guys now before I forget. But how many people we got? Are we all here today? Waiting on a couple of people.
There's 11 in this class.
Sorry, what was that?
There are 11 in this class.
11 in this class? All right. So we got 1, 2, 3, 4, 5, 6, 7, 8. 8. We got 8. It's not so bad. We got a majority of people. I'd love to get 11 though. That's all right. So is there anybody that would like to share? Anybody that would like to share what they've been making in Tinkercad? Anybody want to show us real quick what you got? Anybody? Brad, would you like to share what you made for the class in Tinkercad?
I can share a story about my life.
Oh, I don't know if we got time for that today.
Go. All right.
So, does anybody got any, and even if you just got a couple of spheres or something like that, I know that everybody's trying something new, and so if anybody had anything that they want to share, that they come up. What I'd like you guys to do though in the future is we can go ahead and you can take a screenshot of the stuff that you're making, and then that way we can have something that we can actually turn in that way. So I'll put that together so that way you can use it as a submission thing. I'll assign it, and then you can basically just put your screenshots in it. So then that way I can see to make sure that you guys are doing your work. So if you haven't gotten a jump start on this, please make sure that you're doing that, because what we're going to be working on today is going to be building up on top of some of the concepts that we kind of talked about last time. So last time we talked a lot about this whole concept of size and distance, and then what that means when we try to represent it in like a three-dimensional space between like an X and a Y axis, and then like even a Z dimension. So this week we're going to be doing a virtual lab, and we're going to be working with the tides of the ocean. So being from Kansas, I expect that you probably, if we've got people from Kansas, maybe we got people from outside of Kansas, I don't know. Being from Kansas, I'd expect you to have lots of knowledge of the tide, and not really, right? So the only experience that I have with the tide is when we went on vacation down to Florida a couple of years ago, and we got to the beach, and I got to experience the tide firsthand. So the ocean is just kind of blows my mind in a lot of different ways, but one of those is the whole concept of the tide and about how it continually goes. And so what we're going to be working with today is I've got a virtual lab over tides, and then we're going to find out about what they are and how they function and stuff like that. I've got a video for you guys to watch. We're going to go ahead and start off with watching that, and then we'll come back and we'll talk about some other stuff. So let me go ahead and do a screen share. And let me pull up the appropriate window. And I actually want to do this one. Okay. So this is Crash Course Astronomy, and we're going to be talking about tides.
You know, if Shakespeare had been an astronomer, he would have said that there is a tide in the affairs of the universe, and on such a full sea are we now afloat. He would have been right. You might just think of tides as the ocean going in and out every day, but in fact, what astronomers call tides are a subtle but inexorable force that have literally shaped most objects in the universe. And to understand tides, we start with gravity. Gravity is a force, and it weakens with distance. An important thing to note is that we measure gravity from the center of mass of an object, not its surface. One way to think of the center of mass of an object is the average position in an object of all its mass. For an evenly distributed sphere, that's its center. Right now, unless you're an astronaut, you're about 6,400 kilometers from the center of the Earth. If you stand up, your head is a couple of meters farther away from the Earth's center than your feet. Since gravity weakens with distance, the force of Earth's gravity on your head is an eensy-weensy bit less than it is on your feet. How much less? A mere 0.00005%. And that's way too small for you ever to notice. But What if you were taller? Well, the taller you are,
Hold on.
your head, that probably would weren't dying from asphyxiation and, being 300 kilometers tall. This change in the force of gravity over distance is what astronomers call...
Let's back it up just a second.
Zero, 0.0005%, and that's way too small for you ever to notice. But what if you were taller? Well, the taller you are, the farther your head is from the Earth's center and the weaker force it will feel. If you were, say, about 300 kilometers tall, the force of gravity would drop by about 10% at your head. That probably would be enough to notice if you weren't dying from asphyxiation and, being 300 kilometers tall. This change in the force of gravity over distance is what astronomers call the tidal force. When you have a massive object affecting another object with its gravity, its tidal force depends on several factors. For one thing, it depends on how strong the gravity is from the first object. The stronger the force of gravity, the stronger the tidal force will be on the affected object. It also depends on how wide the affected object is. The wider it is, the more the force of gravity from the first object changes across it, and the bigger the tidal force. Finally, it depends on how far the affected object is from the first object. The farther away the affected object is, the lower the tidal force will be. Tides depend on gravity, and if gravity is weaker, so is the tidal force. The overall effect of the tidal force is to stretch an object. You're applying a stronger force on one end than you are on the other, so you're pulling harder on one end. That'll stretch it. And this is where tidal forces become very important. Look at the moon. It has gravity, but much less than the Earth because it's less massive. It's 380,000 kilometers away, so the gravitational force it has on you is pretty small. And you're pretty small compared to that distance, just a couple of meters long from head to feet. But the Earth is big. It's nearly 13,000 kilometers across. That means the side of the Earth facing the moon is about 13,000 kilometers closer to the moon than the other side of the Earth. This is a pretty big distance, enough for tides to become important. The side of the Earth facing the moon is pulled harder by the moon than the other side of the Earth, so the Earth stretches. It becomes ever so slightly football-shaped, like a sphere with two bulges, one pointing toward the moon and one pointing away. This is probably the weirdest thing about tidal forces. You might expect only one bulge on the side of the Earth facing the moon. But remember, we measure gravity from the centers of objects. The side of the Earth facing the moon feels a stronger pull toward the moon than the Earth's center, so it's pulled away from the center. But the side facing away from the moon feels a weaker force toward the moon than the Earth's center. This means the center of the Earth is being pulled away from the far side. This is exactly the same as if the far side is being pulled away from the center, and that's why you get two bulges on opposite sides of the Earth. The tidal force is therefore strongest on the sides of the Earth facing toward and away from the moon, and weakest halfway in between. Side. A lot of the Earth is covered in water, and water responds to this changing force, this stretching. The water bulges up where the tidal force is strongest on opposite sides of the Earth. If there's a beach on one of those spots, the water will cover it, and we say it's high tide. If a beach is where the tidal force is low, the water's been pulled away from it, and it's low tide. But wait a second, the Earth is...
Isn't that like really cool, guys? When you saw that little picture there of like the tide coming in and then the tide coming out, and you can see how like constant exposure, especially to the water, is eroding away at the bases for these rock structures. And ultimately, someday these are going to just come crashing into the ocean. And so this gives you a pretty good idea of like what it is. Now, also the other graphic that he showed with this, where blue is low tide and red is high tide, gives you kind of like the impression too that even though we show that bulge as being like one uniform thing, you still have different areas of the globe. And why is it like this? Because we're taking a three-dimensional object and we're putting it on a two-dimensional surface.
Stretching. The water bulges up where the tidal force is strongest on opposite sides of the Earth. If there's a beach on one of those spots, the water will cover it, and we say it's high tide. If a beach is where the tidal force is low, the water's been pulled away from it, and it's low tide. But wait a second, the Earth is spinning. If you're on a part of the Earth facing the moon, you're at high tide. 6 hours later, a quarter of a day, the Earth's rotation has swept you around to the spot where it's low tide. 6 hours after that, you're at high tide again, and then another 6 hours later, you're at low tide for the second time that day. Finally, a day after you started, you're back at high tide once more. And that's why we have 2 high tides and 2 low tides every day. Very generally speaking, the ocean tide causes the sea level to rise and fall by a meter or 2 every day. Incidentally, the solid Earth can bulge as well. It's not as fluid as water, but it can move. The tidal force stretches the solid Earth by about 30 centimeters. If you just sit in your house all every day. Incidentally, the solid Earth can bulge as well. It's not as fluid as water, but it can move. The tidal force stretches the solid Earth by about 30 centimeters. If you just sit in your house all day, you move up and down by about that much, twice. Like the saying goes, a rising tide lifts all surfaces. The Earth's spin has another effect. Lag in the water flow means the water can't respond instantly to the tidal force from the moon. The Earth's spin actually sweeps the bulges forward a bit along the Earth. So picture this. The bulge nearest the moon is actually a bit ahead of the Earth-Moon line. That bulge has mass. Not a lot, but some. Since it has mass, it has gravity, and that pulls on the moon. It pulls the moon forward in its orbit a bit, like pulling on a dog's leash, accelerating it. The moon responds to this tug by going into a higher orbit. The moon is actually moving away from the Earth. The rate
Hey, when he said that you go up and down 30 centimeters, that's equivalent to like a foot. So like, that's how much we're pulling. Like literally this right here is how much you're going up and down, like on a given day. So even though you're not experiencing it in a sense, because you're not feeling it, doesn't mean that you're not experiencing it, I guess is what I should say. And so we have this movement that's associated. So when he said 30 centimeters for us, you know, Americans in that sense, if you want to think about America, you know, like we're not going to use metric all the time. 30 centimeters may not be something that you can, you know, easily translate that into something that is relatable to you, but you're talking about almost a foot of difference when he says 30 centimeters. And the whole concept of the moon moving away has got some consequences for us. You should hear this here.
rate of recession of the moon has been measured, and it's something like a few centimeters per year, roughly the same speed your fingernails grow. Now get this, the moon has gravity. Just as the bulge is pulling the moon ahead, the moon is pulling the bulge back, slowing it down. Because of friction with the rest of the Earth, this slowing of the bulge is actually slowing the rotation of the Earth itself, making the day longer. The effect is small, but again, it's measurable. Okay, let's get a little change of perspective. Everything I've said about the moon's tidal effect on the Earth works the other way too. The moon feels tides from the Earth, and they're pretty strong because the Earth is more massive and has more gravity than the moon. Just like Earth, there are two tidal bulges on the moon, one facing the Earth and one facing away. Long ago, the moon was closer to the Earth and spinning rapidly. The moon's tidal bulges didn't align with the Earth, and the Earth's gravity tugged on them, slowing the moon's spin and moving it farther away. As it moved farther away, the time it took to orbit once around the Earth increased. Its orbital period got longer. Eventually, the lengthening rotation of the moon matched how long it took to go around the Earth. When that happened, the axis of the bulges pointed right at the Earth. That's why the moon only shows one face to us. It spins once per month and goes around us once per month. If it didn't spin at all over that month, we'd see the entire lunar surface. But since it does spin once per orbit, we only ever see one face. This is called tidal locking, and it's worked on nearly every big moon in the solar system. Tides from their home planet have matched their spin and orbital period. These moons all show the same face toward their planet. Now wait, which causes tides, and is the root cause behind all these shenanigans. What about the sun? It's even bigger than the moon. Tides depend on the gravity from an object and your distance from it. The sun is far more massive than the moon, but much farther away. These two effects largely cancel each other out, and when you do the math, you find the sun's tidal force on the Earth is just about half that of the moon's. The way the sun's tidal force and the moon's tidal force interact on Earth depends on their geometry, which changes as the moon orbits us. At new moon, the Earth, moon, and sun are in a line. The moon's tidal force aligns with the sun's, reinforcing it. This means we get an extra high tide and an extra low tide on Earth. We call this the spring tide. When the moon is at first quarter, the tidal bulge from the moon is 90 degrees around from the sun's. High tide from the moon overlaps low tide from the sun. We get a slightly lower high tide and a slightly higher low tide. We call those neap tides. The pattern repeats when the moon is full. The moon, Earth, and sun follow along a
Do you Come on.
Closest to us, we feel a stronger effect. If that also happens at new or full moon, we get an added kick to the spring tides. This is called the Proxygian tide and can lead to flooding in low-lying areas. Unless you live on the coast, I bet you had no idea tides were so complex. Tides are universal. They work wherever there's gravity. If two stars orbit each other, each raises a tide in the other. Just like the Earth and Moon, that can slow their spin and increase their separation. Many planets orbiting other stars may be tidally locked to those stars. Near a black hole, where the gravity is incredibly intense, the tides are so strong they would pull you like taffy into a long, thin string. Astronomers call this effect spaghettification. No, seriously, that's what we call it. Today you learn that tides are due to the changing force of gravity.
Is that the same effect that they have in Willy Wonka and the Chocolate Factory? Is that the taffification, where you get stretched out?
Over distance. The strength of the tidal force from an object depends on the gravity of the object and the size of and distance to the second object. Tides raise two bulges in an object, creating two high tides and two low tides per day on Earth. Tides have slowed the Earth's rotation, moved the moon away from the Earth, and locked the moon's rotation in orbit so that the moon always has one side facing us. So,
shout out to my brother for making this video. Totally helped me out a lot. So science just runs in the family, So we all of us just science teachers in my family. We all kind of look the same too. So thanks, bro. All right. So this one right here, right? Crash Course Astronomy. I like this video better. This is a pretty cool one. It's going to be talking a lot about what we're experiencing. So what's really interesting about a lot of this stuff too is let me adjust my windows so it makes it look like I'm talking to you and not just talking off to the side. What's really kind of cool is like around here, we'll get like a weather forecast, right? So you're going to find out like what the temperatures are going to be and what's happening and stuff like that. Now, if we went to somewhere that was on the coast, like I like to go to, we've gone to this little place down in Longboat Key. If I can search for it, and I'll show you here, this is actually the tide chart for Longboat Key. So just like you'd have like a weather map for a particular area, we also have this idea of like a tide chart. And so this gives you the days, and it gives you the times, and it gives you the predicted highs and the low tides. So right now we're here. So we're about noon, halfway through the day. And if you were at Longboat Key down in Florida, this is the height, this is where the tide would be. And we're moving from a high tide down to a low tide. And notice how we have the two high and the two low, remember? So we got here high tide, low tide, low tide. Notice how every 24-hour period in that sense then has these two highs and these two lows. Now, this would be important for you. If you were getting in a fishing boat and you were going off to do whatever, there might be certain waterways that you'd want to avoid or you'd want to take depending on how low or how high the tides are. Because if you've only got a certain amount of feet to work with, in this case, in Longboat Key, it looks like you got about 3 feet difference between the tides. And this is going to change. Let me see if we can't show like a 30-day thing here. Does it give me? This kind of gives you, let's see, can I go forward? Because remember too, the variance in the actual tide is also going to be dictated by where the moon is. So it looks like, it looks like as we process through the month, you're going to start to see that the high and the low tides, there's not that much difference. Now this is that whole understanding of where the moon is in position to where the sun is in relationship to the earth. And so as we go throughout the month, you'll see how this changes. And eventually here we'll get over to the point where we have a lot of these big changes that are taking place. And so, just like the sea is constant in that sense, the tide is also going to give you just a constant change. Now, what's really interesting too about this is that one thing that he didn't necessarily mention explicitly in that video is that these tides are not going to occur high and low at exactly the same time every day. because remember that the Earth, right, is there and it's spinning, but the moon is then also moving around the Earth. And so high tide is not going to be exactly the same time every day. So it's about 50 minutes approximately from one to the next day. So if it was at noon one day, it's going to be at 12:50 the next day. And then, you know, what is it, 50 minutes past that, you know, you got what, 1:40. So it's going to shift throughout the day to match up where the moon is in relationship to the Earth as you're going throughout the day through its rotation. So this is going to be kind of helpful for you. You're going to use this kind of like your weather forecast. It's going to help you with the tide, especially if you're going out in the ocean and doing that stuff. So hopefully you've been at least to the ocean once in your life. If not, you still got a lot of life to live, yo. And so I would put that on your bucket list of trying to get to the ocean at least once, because it is fantastic. It's some cool stuff. And the oceans themselves are different where you go. You go down to Florida versus the coast up in North Carolina or California or Oregon. You know, there's a lot of different stuff up there. So the tidal changes, it's all interacting with the planets themselves, the gravity and the movement. Again, that kind of plays along online with our idea of space and how things and objects move amongst them. So let me go to, I've got your virtual lab here today. So this should be assigned already in the upward bound classroom through Google Classroom. So you should have basically a virtual lab link. So if you click on this link, it should take you to the virtual lab, which I'll walk through with you guys just a little bit here. It's got a YouTube help video. Now this video is different than the one that we watched today. I'm going to be posting this video, and I'll give you a copy of it. I'll dump it in the chat. I'll dump it into the chat for you there too, so that way you have it. You can copy paste it into your browser if you want right now. But that's the link for the video that we just got done watching. The other one that I've got, it's a little bit rougher. It's not as I almost said produced. It's not as finished as the one that we just saw. But they talk about a lot of the same things. And so a little bit of a breakdown for YouTube help on that. And then I've got another one too. This is actually kind of an interesting article. It's talking about, do the Great Lakes have tides? So remember that the ocean is a massive body of water, right? 3/4 of the surface of the Earth is covered in water. And the ocean represents a lot of that. We've got a lot of force acting on a large body, like what he talked about at the beginning of that video. Do the Great Lakes have tides? The Great Lakes are huge. Do they experience tides? Well, this is actually kind of interesting. We've got here, what does it say down here? True tides. Let's see here. It says, studies indicate that the Great Lakes spring tide, the largest tide caused by the combinations of forces of the sun and the moon, is less than 5 centimeters in height. That is that right there. This area right here, less than 5 centimeters in height. So do they really experience tides? Not really. Consequently, the Great Lakes are considered to be non-tidal, but they still experience a change. They still experience a change, just not anywhere on the scale as what you'd have for the ocean. So we've got that for you. And then basically what I've done is I've copied over the table where we got our measurements for the tide. And then I've got some questions for you to answer here. And a lot of these actually were kind of talked about specifically just in the video that we just watched. And then I've got a space here for you to make a bar graph with the data that you collect right here in this table. So again, man, we're hitting it hard this summer with a whole bunch of graphs and a whole bunch of tables and a whole bunch of working with data. You're going to get familiar working with data and going through tables and graphs and being able to read that stuff. And so let me go over here to the virtual lab. Let me see here. Where's it at? I guess I'll just open a new one, new tab. Oh, it was already over here. That's fine. All right, so. And then is anybody having difficulties getting the Flash to run on their computer? I know I'm still getting some people in some of my other classes that are like, I'm still struggling with the Flash, and we were able to help out a student the last class period, be able to get everything working. So if you're having trouble with that, let me know, because I can show you. As just like a real quick recap on that, I'm using Chrome right now. Usually what you'll see is a puzzle piece, or you'll have something that pops up here. If you go to settings, you can search for it. You can literally hit, and you can search for Flash. And then you'll see here, I've got one result that shows up in my site settings. I can click on it, and then it literally says ask first. So if I click on this, which says Flash, the default mode for your browsers should be block sites from running Flash. And so if I tried to then load that virtual lab, if I do that, it should block it. Yeah. I've got it set up. We'll see. Maybe I need to close this whole thing down and then restart it for that to have a big effect on it. But what you want to do is you want to change from the default, from blocking the sites running Flash. I'm going to click that over to ask first. And then that should basically set me up. So I went to settings, and then I searched for Flash, and then I followed that direction. A lot of times too, you'll see something that pops up here. You can click on that to adjust your settings for it as well. So if you're still having difficulties with that, we need to get that figured out, because we're going to be doing some more virtual labs. You're going to need the ability to do Flash. So this is your virtual lab that I've got set up for you. Now, we've got different locations you can choose from. I like the Seaside Wharf. You can have Pete's Pier, Snug Harbor. Give me back to my wharf. There we go. And so, you know, this is also very interesting too, because if you look at like places that exist out on the ocean, right? The piers or these wharfs and stuff like that, a lot of times they'll be built up above where the highest and the lowest tides are capable of coming in, because it would be pointless for you to build a pier out there and only do it, you know, 3 feet up when the high and the low tide for the area is 10 feet. Because then that means that at certain times of the day throughout the course of the month, your entire pier is going to be underwater. And so when we see things like wharfs or piers, you know, in coastal areas, they're going to be built up so that they're protected from the high and the low tides. And so here we've got the Seaside Wharf. And then this is going to help you walk you through what you need to do. The table, I've generated this over in your over here in your spreadsheet, so you can use this instead of using the table that's here. You're going to be recording the lowest tide and the highest tide for different phases of the moon. So we're going to go down here, and it's going to say select a phase of the moon, select a phase of the moon by clicking on one of the 4 circles around the Earth. So I'm going to click this one. It says, observe the water level at 12 a.m. Click the hourglass to begin the day's tide. So, or tide cycle. So I'm going to click here. And notice how it says first low tide. Now this box lights up. I can look over here. This is negative 0.3. I can use these to adjust. And now I can click on this again. I will go through the next cycle. So we're going to go forward 6 hours. And so now we have 9:47 a.m. and this is our first high tide. So we're at 2 meters here. We can then repeat this process. For some reason, this one gets hung up sometimes when it goes from here to here. And so if that happens to you, I'm sorry, but you'll probably just have to reload the page. And then you'll have to start over. For some reason, that box on that particular one, it screwed up with me the other day when I did this, just last hour when I was showing this to somebody else. So you're gonna have to, you might have to, it wants me to select that first. Go through this process. I'm trying to think if there's anything that I'm doing that's messing it up. If I click on that one for the next one, That looks to be 1.7. Notice how now this hourglass is still capable. I can do that and it will move to the next one. I'm going to purposely enter fraudulent information here, and then I'm going to move to the next one. And then we're going to be jumping this one up to 2. And what's really interesting is that when I hit check, it should tell me that I'm incorrect for at least one of them. So let's see what happens.
Check the tide height measurements.
So it took me to this one and it gave me the measurement. It looks like, oh, can I do it? Ah, yeah, so I can click on any of these and it should bring me to that point. So this one's the one that's wrong. So I need to change that to -0.1 here. I hit check.
Congratulations.
There
You
go.
have correctly identified the tide measurements for this phase of the moon.
So then you can go to the next phase, check it out, and so it is as it goes around the Earth. So you're looking at the phases of the moon, you're looking at the high and the low tides. Yeah, so it's a neat little interactive thing for you to try out. And then you're going to be putting this information in here. You're going to be generating a bar graph, and you're going to be answering these questions. So that's what I got assigned for you for this week's stuff. And then also remember, if you haven't done the Tinkercad activities, I want you to be working with that. And so in the last bit of class here, I'm going to explain to you and kind of walk through some of that Tinkercad stuff. Remember that as far as, let me see here. As far as the Tinkercad stuff goes, we were ultimately wanting to make what we were hoping to make is we were hoping to make some stuff like this. I'll have to look back. We're hoping to make some stuff that kind of looked like this with the 3D printer. So what I'm going to be doing is I'm going to make a couple of some generic models like this in Tinkercad that I can then share with you. And then that way you can kind of use them as for your basis for what you wanted. So remember, and what we discussed last week, we were talking about the planets and how big they were, right? And like their size and relatives and stuff like that. And so we said that there was a link that you can enter any date and it would give you the positions of the planets. And so one of the activities that we wanted to do was for you to choose a date that was significant for you for some reason. And what we were going to do is we were basically going to make this model and then we're going to 3D print it out for you. So that way, by the time the upward bound is done, then you guys get that, okay? And so this is kind of like what we'll be going for. I'll make a couple of these generic ones. So if you don't want to make your own, you can kind of use mine and then adjust where your planets are. So I'll create a couple of these that I can share with you in Tinkercad. And then we also then have to decide like what kind of filaments you guys actually want to use, like what colors you got. So I've got some filament that's green. So I've got green filament here. I also have white. I have black filament. I have this filament that's called marble. So this filament is, it is like, let me see if I can show you a good one here. So it's like white, but it has like these little flecks in it. So when you print it out, it's supposed to look like marble, like, you know, like Leonardo da Vinci's David or something like that, where they've actually got like the marble statues. So I've got marble, and then I have like a off yellow golden-ish color, so a yellow gold color. that, let me show you what it looks like. I might actually have, trying to think if I've got, show you. So I have a off yellow golden looking one right there. So this is my little kitty cat that you make when you first print your printer. So that comes preloaded on the printer. So that way you can make your little kitty cat. So I've got this color as well. And I think that we had talked about with the upward bound administrators about potentially trying to get some of this. So this is a glow in the dark filament. So it's kind of got like that off whitish color, and then it will print out your object in this. So that way it can basically charge up in the sunlight during the day. And then when you print it off, it will glow at night. So we have glow in the dark filament too. And I think we had a student in another class request the color purple. So that was also another option. Hopefully we'll be able to get order some of the glow in the dark filament and the purple filament for you guys to use as well. So if anybody else wants a color that's not there, that we talked about already. So we've got black, we got white, we got the marble, we have the green, we have the off yellow goldish color, and then potentially we're going to have the glow in the dark and the purple. So if anybody else wants anything else, we'll have to see about getting some of that filament in. And so I'll make a couple of these, couple of these generic designs that you can potentially then use. And then if you want to just take a look at them and then make your own, but make it approximately the same size, you can do that as well. So work on your Tinkercad stuff, you know, make those models, like those planetary models we had talked about, and then you can use the link that we shared for the last week's homework to get your positions for your planets. So that way you can start thinking about what you want to make as far as like your discs. So that way we can print it out for you. And then what else? Oh yeah. Hey, just in the last bit too. So this is kind of cool. I want to share this with you all. So have you ever heard of this before? So this is a project by NASA that's called Send Your Name to Mars. So NASA has got this Perseverance that's going to be launching to Mars here relatively soon. And you can sign up to basically have your name put on a plaque that's going with the spaceship off to Mars. And so let me find my boarding pass. I signed up for this a long time ago. Let me put it in here. Well, that's not right. And then find my boarding pass. So here it is. So now boarding. It's getting ready to take off July 2020, Mars 20. And what's really neat is that they give you fun stuff like this that you can play with and mess around with. But let me show you. So this is the actual on the craft itself. This placard right here. See these little things that look like stamps? Right here, right here, and right here. So when they open this up, about 11 million people have signed up so far to get their name put on it. And what they've done is they've gone through with the electron beam and they've put everybody's names on these three stamp size objects. So you have to look at it with an extremely small, like, you know, an instrument to be able to read it all. But you've basically got your name put on this that then gets sent with the Explorer on the spaceship off to another planet. So if this makes it to the surface, then my name will be amongst everybody else's names on another object that's off on another planet in space. It's pretty sweet. And so I signed up my whole family, signed up my relatives. I got an uncle that used to work for NASA, I signed him up for a boarding pass, even though he's passed a long time ago. So, you know, it's stuff like this that's also kind of neat about science, right? Because every time we get in here and we talk about science, it's about gravity and it's about numbers and it's about, you know, all these calculations and, you know, all these, like, there is definitely a fun side to science. And there's, you know, if you want to say that there's, you know, there's something bigger than mathematical formulas and, you know, precision instruments and geometry and stuff like that, when you talk about the efforts to put somebody's name on a spaceship that's getting sent to another planet, right? Like, what's the scientific purpose of that? Like, is there really one? Or does it say something about humanity? And so there's a lot of like this whole idea of this passion for wanting to know the unknown, but there's also the journey about how we get there. And this is part of it. And so I know a lot of times in school, you're just going to cover a lot of dry science stuff because we have to teach you a bajillion things within a certain amount of time, and we got to test you on them all. But I promise you that there are people out there that do projects like this that kind of still, you know, the soul of science, you know, is still, if you want to use a term that's kind of like a misnomer in that sense, like there is still wonder and there is still something to be said about the quest. And so things like this remind me of that. And so if you want to sign up, you know, the next one that they're sending off here should be coming up within, I think about, what is it, like a year? I think they're going to go and do another one, or it might be as soon as January. So you can actually sign up for the next flight. So this one, out of all the people on the planet right now, about 11 million people signed up to put their names on there. You know, for the next one, it looks like we've got 431,000. So I'm going to sign up for the next flight, you know, and then you're going to go with that and send my name to Mars for the next one. So if you want to participate in this, it's pretty sweet. I'm going to put this, I'm going to copy this over and I'm going to drop it in the chat. So that way you have access to this. So that way you can sign up your family if you want, talk to people about it. And it's a good way to just kind of talk about, you know, like, I mean, right now everything in the world is kind of like dicey, right? But you know, people are still planning for big leaps and fun stuff in the future. So this is a fun activity you can do. And get your name on a freaking spaceship that's going to Mars, right? Like, your name's gonna be on there. It's cool, you know? So definitely you need to do that if you want to. If you want to. I definitely gonna sign up for the next one because I'm gonna get some more frequent flyer miles. I think NASA is actually keeping track of this as kind of like a like a funny side thing where it actually keeps track of like your frequent flyer miles and stuff like that. So you know, just something fun for you guys to check out. Hey, so I'll be hanging out in the office hours Zoom classroom thing at 1 o'clock. If you guys have any specific questions about the stuff that you've been assigned. Other than that, just keep on working. We're about week 3, so we're about halfway through, right? And so we kind of got the cycle now where we got basically a virtual lab, some fun stuff to do, and then just a little bit of lecture on stuff. So make sure that you guys are keeping up with the Tinkercad and that you got something to show me next time we start class, okay? I want to see something, all right? So, all right, everybody, have a fun week, and I'll see you later. I'll actually see you in an hour if you need help with anything. But thanks, everybody. Good to see you. Bye.